All right. Hi, everyone. I'm Joey from Yelp, and today I will be talking about taking Datastore fleets and automating them primarily with Puppet. And yeah, so before I do that, let's get started with a little bit about what Yelp is. I mean, I think you guys might be familiar, but if you're not, Yelp is a company that connects people with great local businesses. And we have a ton of content. So we have about 92 million unique monthly visitors on mobile. More than 108 million reviews have been contributed since conception. 72% of searches to our website come through mobile devices. And about 32, we're launched in about 32 countries. So needless to say, we have a lot of data challenges associated with this. But what about me? I mean, if you're going to trust me, why would you trust me? Or maybe you wouldn't trust me. I've been at Yelp for a little over 4 years, and I've been a core contributor to our data platform. So kind of moving Yelp from a kind of monolithic MySQL data tier into Polyglot, multiple different data stores, Cassandra, Elasticsearch, Zookeeper, kind of like best data store for the job. And along the way, I've had a lot of fun writing engineering blog posts about how we do these things at scale. So a lot of the things I'll be referencing today, I've actually talked about on our blog in way more detail. So if you're interested, definitely check that out. And yeah, all right. So to kind of set the scene for why you might want to build automation on your data stores, let's first take a look at kind of what I call like the classic 3-tier. So the classic 3-tier is like presentation, logic, and data. But nowadays, we don't just do that, right? In your presentation tier, you've got 22 different web frameworks. You've got iOS, Android. You've got a bunch of different tiers in your presentation. But then on your logic, you've also got like 120 microservices running different languages, maybe like Java, Python. At Yelp, we primarily run Python and Java, but we do spread that out across multiple different kinds of deployment systems. So for example, we have our POS that runs on Mesos and uses Docker and all that fun stuff. But we also have kind of older services that maybe get deployed manually. And everything has to work on both data centers and clouds, because Yelp runs a hybrid architecture. So that kind of specialization in the logic tier also then causes a specialization in the data tier. And Yelp runs tons of data stores. There are just a couple of them. But you might ask, why would we do this? Why would we make these choices? And the answer to that, I think, is that as your product gets more complicated, you're going to start having kind of verticals in your product. So here's an example of, I know this looks kind of crazy. It's supposed to. It's kind of unfortunate. How many of you guys have something that looks a little bit like this when you actually draw it out? Anybody? Yeah, OK. All right. Very honest. And this is, I think, one of the motivating reasons for having a Polyglot data tier, because you need to kind of optimize each of these flows. So like, for example, your search flow is probably not going to use MySQL as a backing data store. And your logging flow is probably not going to use MySQL. So you can't really just deploy one data store anymore as you try to kind of squeeze every ounce of performance out of each of these verticals. So I guess suffice to say, it's complicated, and that's why I'm having this talk. All right. So when you really get down to it, Yelp's data store problem is that we have to be able to support a lot of flexibility across that data tier. So we must be able to support different data stores, all those data stores I listed before, Kafka, Elasticsearch, Cassandra. Within those data stores, we have to be able to support multiple different configurations of those data stores. So different tunings, different clusters, different use cases. Any solution we choose has to be cloud and data center ready. Very importantly, our solution has to be ready for production. So we're not going to use something that got released alpha in Kubernetes last week. We're going to use something that's been around for a while. And I think this is possibly the most important criteria. We have to be able to cope with data gravity, which is kind of this notion that data is very hard to move around. And all of your application logic kind of revolves around that. So this is like a kind of pithy picture, I think, of all of your apps kind of falling towards your data. And so when we're kind of looking at potential solutions to this problem, we've got to keep this in mind. And I think that for us, this is kind of one of the reasons why we disqualified a lot of the standard POSes for data stores. Because in my opinion, a lot of those things like Mesos and Kubernetes, they don't do a great job of dealing with data gravity. They don't do a great job of ensuring that your instance of Cassandra won't just randomly get killed, and then you'll lose all the data on that node. Relatively recently, they've started to work towards solving this. But at least at Yelp, we found that Puppet is the much more reliable choice when trying to automate data stores, because it's a kind of, I mean, let's be honest, it's been around forever, and it works. So the rest of this talk will be kind of talking about how we make it work with Puppet. All right. So let's kind of go through that checklist. How are we going to support different data stores? Well, at Yelp, we've developed what we call cluster modules. So most of your open source Puppet modules on the Puppet Forge are going to be focused on configuring a single instance of a data store. So for example, the Elasticsearch module focuses on configuring a machine to run Elasticsearch. What we found is it's better to think at a higher level of abstraction than the vendor modules. We concern ourselves with configuring clusters. And you'll notice that all of the signatures are kind of the same. Like they're a little bit different, but in general, everyone takes a cluster name, maybe a role, and very importantly, a team. And under the hood, they look something like this. Let's kind of start at the top and move to the bottom here. So every module that we run, every one of these wrapper modules, starts with per module hire data, which is new as Puppet 4. We've been using it as a plugin since Puppet 3. And I'll explain in a bit how that enables a lot of this kind of configuration diversity. But then furthermore, we have files that are per cluster. So each one of those cluster names can drop their own custom files. This is very important, for example, if you want to enable things like Kibana on an Elasticsearch cluster. Well, you need to drop some files on disk, and you need to enable some custom code. And that actually comes down later with the manifest directory, where we have per cluster enabled manifests. However, the vast majority of the automation is going to happen in the server and monitoring configuration directories. So within the module, we have this little monitoring subdirectory, and that includes all of the kind of cluster-wide monitoring checks. And then within the server one, this is kind of where the vendor modules start coming in. So within the server sub-module, that's where you would configure things like actually include the Elasticsearch vendor module, or in our case, like tie into all of our existing Puppet automation. So like Yelp server.pp is kind of our manifest for including all of the Yelp-specific stuff on a box. But all of the things operating at the per instance configuration lives in that directory. Of course, we have tests, and then finally we have templates. So I'm going to the rest of this talk, we'll be kind of walking through these and kind of explaining what each of these components brings and how you can use them to automate your data stores. And I should mention that every Elasticsearch cluster or Cassandra cluster, every X cluster module follows this general pattern at Yelp, and it's very powerful. But why is it very powerful? Well, it's really powerful because it allows you to support different configurations on your clusters. And the reason why it does that is because your data store configuration generally doesn't change by the same things that your traditional Hira might change by. So like your traditional Hira might be organized by like Datacenter, availability zone, region, and so on. But that's really not how you want to organize your data stores configuration. So here's a snapshot of a Cassandra configuration file. And you can see that I've highlighted all the things that have to change and what they have to change by. So there's certain things that you have to change per version of the data store. There's certain things that you might have to change per cluster of the data store. There are certain things you might have to change per instance based on things like how many CPUs or how much RAM. And then there's the occasional overall default. But what we found is that functions do help here, especially with those node configs, but hierarchical config is even better. So this is an example of what kind of module hierarchy we're using. So this is a Puppet 4 module hierarchy for Hira data, which is specific to just the Cassandra module. So this isn't AZ or anything. It's not overriding our, we're not using the overall Hira in our Puppet config. Instead, it's using this one. And you'll notice that the hierarchy here matches that kind of notion of how we wanted to configure our data stores. So at the top, we've got the specific config to the cluster, followed by the config for the version of that data store. So for example, Cassandra 2.2 versus Cassandra 3, which are going to have different configuration options. And then finally, with those overall defaults. And to kind of see what that looks like on production, this is a snapshot of our module Hira snapshotted out of prod. So you can see that for every cluster that we deploy, we have a little YAML file. And then those can be configured independently by teams usually. So a team at Yelp, like the search team or the ads team, so totally not related to infrastructure, they would commit this little YAML file in the per cluster because it doesn't contain very much config. The vast majority of the config lives in the version defaults, which we as the platform owners add. Because that's the majority of config. Most people don't need to tune that much. But this does give them the ability to tune that per cluster, which is very powerful. And to kind of give you another example, so we saw the hierarchy for Cassandra. The cool thing about having the per module hierarchy is that you can use a different hierarchy for each data store. So for example, Elasticsearch, which has per role configuration. So you have like dedicated master nodes or dedicated routing nodes. We can change the hierarchy for that. And we can make it so that we can tune configuration for just the dedicated master nodes or just the dedicated cluster nodes. But very key to this, we didn't have to add this to our overall Puppet hierarchy. We just had to add it to the Elasticsearch module. So this allows us to support that kind of per data store configuration that we really need in order to provide the service that our customers expect. But what does one of those per cluster YAML files look like? What does it actually look like? Well, this is all that it is. And in fact, the mandatory interface, the thing that our developers have to specify in that file, is only those top 5, right? Like, any of us, we could fill out a web interface that says, which version do I want? Which team is responsible for this cluster? And should it page us or ticket us? Like, some things in development don't need to page us. Some things in prod maybe need to page us. So this is the entire mandatory interface that a developer has to supply at Yelp to get a cluster of a data store cluster. That's it. And the way that we're able to achieve that is through that hierarchy. But even more that I think is pretty cool is that this particular cluster decided, hey, we really need dynamic scripting in Elasticsearch. So all they had to do to enable that was add this one little override here, and then add the, in their case, they want to write their scripts in MVEL because that's what they have. So they say, hey, can you please install the MVEL plugin as well? But what about, where'd all the rest of the config go? Like, if any of you guys have configured Elasticsearch, the configuration isn't just that one option, right? There are like thousands of options for the Elasticsearch. Well, the key is that comes from the hierarchy. So here's an example of all of the config that we have throughout the hierarchy. So you can see that very few things, this is actually Cassandra, just to show you guys that we use the same system for every data store. So whether it's Elasticsearch, Cassandra, Kafka, et cetera, we use the same general system. And you can see here that the vast majority of the config goes in the version, which the developer didn't have to specify. They just said, I want that version, and then they get all this config for free. These are all like sane defaults for that version of the data store. But what they do specify and can control is the per cluster one. And in this case, for example, the Cassandra cluster wants to do encryption. So they specify a couple of options for client-side certificates. So this is that kind of flexibility that I've been talking about, where the developer doesn't have to think about all of this config. They just have to think about their cluster and what they need. But they still have that ability. So I think that that's really cool because you don't want this kind of hierarchy in your main hierarchy. For example, like before this, we used to kind of just add some of these, like base and cluster. We used to just add these into the main hierarchy. But what would version be? Because like you can't just have version because you might have 2 data stores that have the same version, like 2.2 in Cassandra versus 2.2 in Elasticsearch. So you can't just add that to the hierarchy. You start having like Elasticsearch version and Cassandra version and Zuki, and then your hierarchy file starts getting polluted by these. So I think that this is a much better design, and we've been using this for about 3 years very successfully. All right, but let's actually, I actually want to know, though, how does this config get onto a config file on disk, right? Because it's one thing to be like, oh, yeah, like we can merge, we can define it like this, but it's not useful unless it can actually materialize itself on disk for your data store. And the first step to that is a great function called hire hash. You can also, in Puppet 4, you can just do lookup with a merge behavior. But basically what this does is instead of looking up the key at the highest level of the hierarchy, it merges the value of that key from all of your hierarchies. So for example, this key, which is the config for the Cassandra.yaml file, it gets merged. All of those different levels get merged into one with higher levels taking precedence. So for example, if they override something in the cluster.yaml, that takes precedence over that in the version or the default. But you still end up with a hash that contains all of the keys. So after you've called hire hash, you have a full configuration dictionary for, a full hash for Cassandra.yaml. But you still have to get it to disk. And the way that we've done that is a little bit of a hack, but basically we have a template which dumps the keys to a YAML file, very importantly in sorted order. So this is something that we learned early on, was if we just used the built-in Puppet, take this hash, make it into a YAML file, we couldn't guarantee that the keys would be ordered. And that was problematic because whenever a developer changed a config option, the Puppet diffs were like very difficult to code review and make sure that they were reasonable. So with this little hack, we're able to ensure that we write out a full YAML file that also can do things like understand data notation. So like the default implementation of the dump to YAML can't understand things like a.b.c is equivalent to a:b:c. So with this little bit of a hack, we're able to get this very powerful generation of config. And I think this is really cool because it allows you to think in those higher levels of abstraction. But at the end of the day, for all your data stores, this is how the Cassandra.yaml or Elasticsearch.yml or Kafka.yaml, this is how those configuration files are generated, all in the same way. And every module can reuse this functionality, right? Like this isn't specific to Cassandra. So therefore, every time you add a data store, you can just reuse this functionality and you get it for free. So that's how you get to the actual Cassandra file on disk. But where do functions come in? Because some of these things, some of these configuration options do have to change depending on the machine. And what we found is that functions are awesome for this. This is why Puppet 4 wanted to have the ability to have functions back higher data before they merged module higher data. Because functions are very important for this kind of per machine configuration. And at Yelp, when we're writing these data store modules, these cluster modules, we kind of have this rule of thumb of like never hard code anything, because you can't guarantee that data store will be deployed on the same type of hardware that you tuned that particular value for. And what we found is that any function is better than hard coding, even if that function isn't perfect. So for example, here, I wrote a function for guessing the off-heap size of mem tables for Cassandra. And like I just admit in a to-do, like I have no idea if this is the right algorithm for assigning this. Like Cassandra upstream doesn't recommend any algorithm. Usually the upstream data store provider will be like, oh, set it to this, follow this formula or follow this algorithm. In this case, they don't, so we just picked one. And it might be suboptimal, but the nice thing is that if we ever figure out it's suboptimal, we change it once in the function, and then it gets propagated to all our clusters. So it's not something that we have to be like, oh, we set that option for these 3 clusters, and we have to remember to go change it for those 3 clusters. And honestly, sometimes it can be as easy as just using a custom fact, like, or not even custom fact, just a fact. For example, like sizing thread pools on data stores is often just like set it equal to the size of the processor count times some constant. So these functions plus the hierarchical config is really what gives us the ability to flexibly configure our data stores across different data stores and within a kind of data store within different kinds of clusters. All right, so I've shown you how we can support different data stores, and I've shown you how we can support different configurations within those data stores. But what makes a cloud and data center ready? Well, at Yelp, we support both cloud and data centers, and we support them a little differently. With data centers, we just use the standard DNS, little bind config. We have Elasticsearch nodes, and then we have a node rule. And I mean, this does work. This did work for a little while. But honestly, like this is a little sad kitten, right? For every data store, I have to write these kinds of mappings that at the end of the day end up instantiating that Elasticsearch cluster module at the bottom. But along the way, we've done things like parsed out the the client cert and done horrible. This is just, I'm not a big fan of this. I'm a much bigger fan of what we did for Amazon in the cloud. What we used for in the cloud was we used ENC. And to kind of paint the picture there, this is how we launch a cluster in Amazon. So we pair Terraform with Puppet. So we use Terraform. With about 42 lines of Terraform code, we're able to kind of infrastructure as code, if you will. We're able to declare we want an ASG that launches nodes. And then the important part is this little tag at the bottom. So way down here at the bottom, there's this 3 lines of code, which says when you launch instances, tag them that they should have the Cassandra Puppet role. And that's all the glue we need in order to tie into that Cassandra cluster module that we talked about earlier. But how does it actually get there? Well, it gets there using external node classifiers, which are, I think, a maybe underrated. They're really awesome function of Puppet, which allows you to essentially, instead of using those node declarations, you can write a script which, from external information, deduces which Puppet classes it should apply. And so, for example, we've written one for EC2 and GCE. They're good open source external node classifiers. There are also external node classifiers for data centers. So if we were going more hardcore down the data center route for data stores, we might invest in replacing that kind of hacky DNS solution with this. And the reason why this is awesome is because it decouples the aspect of provisioning your hardware from configuring it. So you write that one thing that says provision this cluster, and then as it launches nodes, it tags them with little Amazon EC2 tags. And then Puppet just automatically does the right thing. So when those nodes come up, they use ENC to find which module they're in. And then that option gets injected into the role. So that's the only glue we need, that one option pass. That's all that the provisioning system has to know. And then from there, that hierarchical config that we talked about earlier takes over. So because remember that all we needed was the cluster name, and once we had that, we had the cluster file, and once we had the cluster file, we had the version, which meant that we had all the other config. So I think that this has been awesome for us. It's allowed us to scale to really great amounts of configuration. And just to show you that, I want to show you how this is production ready. So at Yelp, we use Puppet to manage data stores. We manage about 100 clusters with over 500 data store nodes. Our runs take about 5 minutes to apply these, to run these ENCs and to apply the right config. We run Puppet continuously, CI/CD. We're only every hour. I guess now the recommendation's every half hour. But I think that the important bit is that we actually don't run most of our automation through Puppet. We use Puppet to drop the automation. And that's what I'm going to talk about now, is kind of how do we do that. And just to really prove it to you guys that we use this in production, here's a fax of Cassandra clusters. So we're running 146 Cassandra nodes over 13 clusters. We're running 228 Elasticsearch nodes over 27 clusters. We're running 96 Zookeeper nodes over 28 clusters. And we're running 102 Kafka nodes over 25 clusters. So this really does work. We've been doing this for about 3 years. It works fantastically. And we're able to tune each of these clusters individually as we need them. But it is an 80-20 thing, where 80% of the clusters don't need any tuning. They just use the defaults. But 20%, we support that additional amount of configuration. All right. So it's not done until it ships. It shipped. It works. But it's also actually not done until it's monitored. So let's talk a little bit about that. How are we going to use Puppet to monitor these data stores? Well, the answer is that we don't fully use Puppet. We do, at Yelp, love our Puppet monitoring check, which integrates with, it's a Puppet module that creates Sensu checks. And these go in that monitoring subfolder of the cluster modules that we saw earlier. But I just want to call it a couple of things here, because one thing that I think is really cool about this is that because we know the team that's responsible for the cluster, all of the monitoring checks can automatically go to that team. So to me, this is DevOps, is giving developers the ability to automate their infrastructure, but also then holding them responsible for the infrastructure they've created. And for example here, when they run their Cassandra cluster out of disk space, they're the ones who get the page, because they're the ones who have the context for, oh yeah, I just pushed that change that wrote 10 times more data to Cassandra. However, there is obviously the second step, which is when they get the page, they're not a Cassandra expert. So we mandate that every check that goes into one of these monitoring checks has a runbook link. This isn't an optional field. Every check has to have a runbook, and every check has to have that context for the developer taking the page. So I think this is pretty cool. But what's really cool is when you start thinking about, just like we took a step up in the level of abstraction from the instance configuration to the cluster configuration, we're going to do the same thing when we're monitoring Cassandra clusters. And just like you don't monitor an individual Docker container that's running on Kubernetes, you monitor the health of the application, we're going to do the same thing with Cassandra or Elasticsearch. And some of your data stores come out of the box. Like Elasticsearch comes out of the box with this great little endpoint that you hit, and it says, yeah, I'm good. Cassandra, a little less so. But that's OK, because we can automate that. So here's an example of 2 Cassandra rings. Cassandra is a data store that uses consistent hashing to apply the data across the ring. And our monitoring, when we're thinking about these 2 rings, has to be able to differentiate between this. So on the left, we have a single node failure. And on the right, we have 2 node failures. And on the inside of the ring, I've colored how many available replicas of a given data set or a given key there are. And the difference is that the one on the left can still complete client operations, like quorum, for example. But the one on the right can't. So we have to make our monitoring intelligent enough to be able to tell the difference between this. In general, there's no one answer fits all for every data store. And so in this case, I've actually written a blog post about how we monitor the health of Cassandra as a cluster. But where does Puppet come in? Because I would say that while it's totally cool for us to say, yeah, that's good and that's bad, is this logic that we should have in Puppet? And I would argue that Puppet ideally doesn't have this logic, but it does drop the automation. So for example, at Yelp, what we do is we use Puppet to drop cron jobs, which execute this command. So this command is, it's provided by a Debian package, the Cassandra tool Debian package that we build. and it's the check Cassandra cluster. So we use a general purpose programming language like Python or Ruby to build the monitoring check, and then we schedule it via cron or sensu initiated by Puppet. And this is going to kind of be a pattern of the rest of this talk is we use Puppet to drop the automation, but we don't necessarily use Puppet to run the logic. And the reason for that is because you can't always guarantee that Puppet will be running on these data stores. You can't always guarantee, especially when developers start being able to like change Hira, you can't always guarantee that the Puppet catalog will compile. And there's a whole bunch of information about like how do you, there's a whole bunch of interesting information about how do you actually communicate to developers, hey, you've broken Puppet on your cluster. But we just like to avoid that entirely for critical things like monitoring. And we just rely on the boxes to run cron, which is much more reliable. This sounds kind of silly though, right? Cron is like from the 1970s, right? Like why would we use cron? And the answer is because it keeps it simple. And Yelp is a huge fan of dropping cron jobs with Puppet. In fact, we've open sourced a Puppet cron module, which adds a ton of very useful kind of like wrappers around cron. So for example, here I just want to call out things like staleness checks, where we can say if this cron job, if this automation hasn't succeeded in some amount of time, alert us. And we can do things like have timeouts, where we can use operating system provided functionality to say, guarantee that if this cron job doesn't finish within 3 hours, you kill it. And this is the kind of guarantees that allow you to build very robust monitoring and automation. But at the same time, it's very easy to understand. So that's how we use Puppet to monitor these clusters. Namely, we use it to drop automation. But what about the next step? Because it's not actually done when it's monitored. It's done when it's monitored and integrated into your production infrastructure. So how are we going to do that? Well, at Yelp, integrating with production infrastructure and being available to developers means working with our service discovery system. And at Yelp, we treat our data stores just like we treat any other service, which means that we're going to discover our data stores with SmartStack. So SmartStack is an open source project consisting of 2 components, Nerve and Synapse. And we use Puppet to, for example, drop Puppet drops every box on that, or every box in this diagram. So Puppet drops the Nerve daemon, Puppet drops the configure Nerve cron job, Puppet drops HA check, and so on and so forth. But the actual data plane of doing service discovery is then separated. So again, Puppet is the control plane, and then the data plane is something that we can be a little bit more confident is running all the time. But I just want to take a step and just kind of like say this is really cool, because from a developer's perspective, they think of data stores just like they think about any other service. And this enables the same amount of that kind of versatility that you see from those POSes, where like services come up and down. Same thing is true for your data stores. As data stores come up and down, they register, deregister, and developers discover them through the same code paths that they would discover other services. And the reason why you particularly want to use this co-process design with data stores is that you can't guarantee that any data store you're deploying will use your service registry system. So for example, if you're a Java shop and all of your services register using like Twitter's registration library, right? Like you can't build that in to MySQL. But if you use a co-process, which does the health checking separately to do the registration, then you decouple those 2 things. But again, how is Puppet coming in? Well, Puppet drops everything on the diagram. But in addition, Puppet is actually the thing that says, oh, this node is a member of the Cassandra this cluster service, or Elasticsearch this cluster service. And what we've done is we've created a custom type called a Puppet service, Nerve simple, so Nerve Puppet service, and this is all you have to do in a Puppet module at Yelp to get the box that's running that Puppet code to register in our service discovery system. That's it, that one line. And you're registered in the service discovery system. And the way that works is by hooking into the cron job. So this configure Nerve cron job runs constantly. And one thing it does is it checks this well-known directory for files, for service names. And so that custom type is not very complicated. That custom type is essentially just saying whenever we define that, please drop a file in this directory called the service name. So again, Puppet is the control plane, not the data plane. The data plane is this configure Nerve cron job. But we can see how Puppet enables that automation. And just to prove that really works, here's an example of any Elasticsearch or Cassandra cluster. Those discovery files will show up in this directory. And here you can see these are nodes that are running Puppet that have registered in SmartStack. All right. So I hope I've convinced you guys that you can use Puppet in production to configure data stores. But if I haven't, let's take a step back and consider that last hardest problem, that problem of data gravity. Because this is why I kind of like advocated for Puppet over anything else. And that's because if you lose your data, your company stops being a thing. Like, you know, if Mesos decides to undeploy your entire MySQL cluster and you no longer have a MySQL cluster and you've lost it, well, that's a bad day. And especially if you're in a cloud environment. So we get these tickets all the time where it's like Amazon has decided that it's going to, who else has Amazon just tell them randomly, hey, we're going to kill your instance? Yeah, OK. This is a bad day, especially when you're talking about mission critical data. But that's OK, because we can use what we've learned about dropping that control plane. And at Yelp, within those tooling packages that I talked about, we implement this little handle AWS lifecycle events endpoint. And what that does is it hooks into a system from Amazon where Amazon will give you a heads up when it's about to scale down or scale up an ASG, when it's going to terminate your instance. And the nice thing about this is you can delay it. So you can be like, hey, Amazon, give me 48 hours to get all of the data safely off this Cassandra node. And this is all implemented. I mean, this is custom per Datastore. So Elasticsearch, for example, is very easy, whereas Cassandra is a little bit more tricky because you have to make sure that you're not ruining consistency as you do that. But the key here is that it's this little piece of tooling that actually does the registration. But how does Puppet come in? Well, again, Puppet drops the automation. So that automation we write using our standard CI/CD, or sorry, standard flows, and it's deployed with our standard CI/CD. And at the end of the day, we end up with a Debian package, which Puppet can then install on all of our Cassandra, Elasticsearch, Kafka, et cetera. And then in addition, we then cron up those auto-scaling event handlers. So those cron jobs, which every 30 seconds say, hey, Amazon, are you going to terminate me? Or hey, Amazon, do I need to move data around in preparation for somebody joining the cluster, for example? And you'll notice that we're using some of those advanced features that I talked about. So for example, we're using locking to ensure that only one instance of that cron job can be processing those auto-scaling events at a time. This is very important. You don't want two of those things running at once and then accidentally making bad choices as a result and bringing down your data store. That'd be a bad day. But also we know via staleness checks whether or not we're able to process these. So this is really important because if you're unable to react to that event, you want to give your operators a heads up, like, hey, I'm going to go down in 24 hours, but I was unable to process that event. I was unable to successfully move the data off, and then an operator can intervene. And very importantly, from before, an operator who's on the team that cares about that cluster because we have that ownership information threaded through in the HIRA. So an operator who cares about this cluster will get a little heads up like, hey, I failed to process auto-scaling events, and I'm about to die in 24 hours. Just heads up in case you care. And usually developers will be like, oh, I care about that, and then they'll go fix it. So that's pretty cool. But you can also do things like backing up your data. So here's an example of how we use Puppet to drop a cron, which uses a snapshotter, which is installed through a Debian package. So again, Puppet installs the automation, but isn't necessarily the full story in and of itself. It's the control plane, not the data plane. So here's an example, and we're using some other advanced features of our cron module, like, for example, if a backup doesn't complete in 3 hours, we assume it's stuck, because sometimes it gets stuck. And that's fine, you just kill it, and then the next iteration of the backup will finish off where the previous one failed. And then if we don't complete within 49 hours, I'm not entirely sure why 49 hours, but instead of 48. But if we don't complete within that amount of time, we let someone know, say, hey, this cluster isn't backing up. And this can be tied to, for example, the cluster's SLA on how much data you have to retain in backups. So I think that's pretty cool. All right, so I've kind of walked you guys through a lot of different ways that we configure data stores. And I just want to take a second to kind of step back and recap about kind of end-to-end, how would you use this? How could this be useful? And really, the first half of this slide, or the first half of this talk, can be summarized by this slide. So what do? We use Terraform to launch nodes which have tags. Those inform external node classifiers, which inject just enough information into our cluster modules to get them started using their HIRA hash functionality, which then is able to fill in all the rest of the configuration, template it out to disk using templates, configure everything per node with functions, and then end up with an actual running instance of the data store. So this picture is kind of, I think, like a good overview of if you're interested in replicating this kind of thing, what are the components that you have to build? But then second, I think what I've spent a lot of time talking today about is using Puppet to enable your automation. So it's not necessarily having Puppet monitor your data store. It's not necessarily having Puppet doing service discovery or having Puppet run your backups. But it's using Puppet to drop your data plane to do all of those things. So at Yelp, we use cron. You guys can use whatever you want. But I think that it's a very powerful paradigm and one that gives us that ability to deal with that data gravity. Because we can very reliably assert that these components work because we're using them everywhere in our infrastructure. And I think that's, again, maybe the second takeaway from this talk is treat your data stores just like you treat the rest of your infrastructure. They should register in the same place. They should be monitored the same way. And developers should interact with them just like they interact with other services. So yeah, that's all I've got. If you guys have any questions, I'd be happy to take any. Any questions? It was either thoroughly confusing or completely clear. Hopefully the last one. Somewhere in between? All right. What was the confusing part?
It's just a fire hose.
Okay.
It's just a lot to digest. But the overall concept was very clear.
Cool.
Very intriguing, actually.
All right. Yeah.
Are you running this with Puppet Enterprise or just
Are we running this? The question was, are we running this with Puppet Enterprise? We're running this with open source. Yelp does all open source Puppet, mostly for reasons concerning like scalability over the number of nodes. I'm not entirely sure about that, to be honest. But in the case of data stores, it does all we need. Like open source does all we need. So. Cool. All right. Fantastic, guys. Thanks.
Thank you, Joseph.